Hi, today I want to talk about rational numbers with dots. This video is targeted for an audience that already know what rational numbers are, but is not quite familiar with repeating decimal representations. So let's get started. 1/4, 5/8, or even negative numbers like -3 divided by 2 are rational numbers. In our daily life, we most likely express those numbers in their decimal representation. For example, 1/4 is commonly known as 0.25 or 25%. However, other fractions like 5/8 are not common knowledge, so we always have to calculate them to get their decimal representation. We do so by dividing 5 by 8. 8 doesn't fit into the 5, so we will start with 0, and the result will be 0 dot something. So we will subtract 0, and now we pull down a 0. We can pull down a 0 because 5 is not only 5, it's also 5.0000, like 5 meters and 0 centimeters, or $5 and 0 cents. Now we can calculate again, how often does the 8 fit in the 50? We will see 8 times 6 equals 48. If we subtract 48 from 50, we will get 2. 2 is smaller than 8, so we did something right, but we are not finished. We have to pull down another 0. Check again. 2 times 8 equals 16. We will subtract 16 from 20. We will get 4, pull down a 0, and we see 5 times 8 equals 40. To subtract 40 from 40, we will get nothing, which was perfect. Now we are done. We have found a finite decimal representation of 5/8, which is 0.625. This way to calculate a fraction can be quite complicated. So there's another way, which I will show you in the other example, -3 divided by 2. If we write as a fraction, we usually write the minus in front of the fraction, which would look like this. Now we use the fraction rules and expand the fraction. So we will multiply the numerator, which is the upper part, and the denominator, which is the lower part, by the same number, for example, 5. Now we get a different looking fraction, namely -15 divided by 10. Even if it looks different, it's still a representation of the same number. So we have multiple representations of numbers. The nice thing about that representation is that we can easily calculate it in our head, because the 10 is just moving the decimal place of the dot or the point. So the result will be -1.5. As far so good, but then more fractions. For example, -1 divided by 9 and 2 divided by 3. Those fractions can't be expressed as a finite decimal representation. Let's try it out. If we divide 1 by 9, we'll see we need a 0 because 1 is smaller than 9. And we write down 1, pull down a 0, and write a dot. Then we subtract 9, because 9 is the maximum that we can put in to the 10. If we subtract 9 from 10, we will get 1. If we pull down 0, we will get a 10. Now we can write down another 1 and subtract another 9. We get a new 1. If we pull down a 0, we get a 10 again, and now we see we have a problem. We can do this forever. You can always write another 1 behind the dot and pull down another 0. So we will never finish our equation. So we could write down 0.11 ... We don't have a finite decimal representation, but a repeating decimal representation of that fraction. The same is true for 2/3, which I would do by the other method, by expanding with the factor 3. Now we get a 9 in the denominator, which is not 10. However, 9 is quite helpful because we already calculated 1/9. So we can say the fraction is 6 times 1/9, and 1/9 was 0.11111. So our result must be 0.66666. Mathematicians don't really like these dots, so they usually write it with a bar over the 6. So it's 0.6 and this periodic sign over the 6. So let's clear everything up and look at the numbers again. Seeing all those numbers, a question that occurred to me was, are there more rational numbers that can be expressed as a finite decimal representation, or are there not more numbers that can be expressed as a repeating decimal representation? Similar to the normal numbers, you can't write all of them down. But similar to the normal numbers, you can also start writing them down. Like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's a way to write down the rational numbers. This way starts with 0, or better 0 divided by 1, which is the rational number, then goes to 1. Rational numbers are positive and negative, so we will go to -1 next. However, we could do a little detour and increase the denominator by 1 to go to 1/2, then back to 0, then to -1/2, then to -1. For -1, we can go to -2, then over a detour, we will go to +2, and from +2, we will reach 3, and so on and so on. The fact that we could write all the numbers down one by one is mathematically really, really powerful, because it actually says that the same number of natural numbers then through rational numbers, which is quite interesting. Both of them are, of course, infinity, but the kind of infinity is countable infinity, it's the same. So let's take a look at the number we have drawn. We can see from left to right the dividend, which I previously called the numerator. Dividend is just the Latin term for it, is increasing by 1. So, and in the other axis, the divisor or the denominator is increasing by 1. So we get something similar to a coordinate system. And on the horizontal axis, we have all the integers, like 1, 2, 3, 4, 5, 6, 7, but also the negative integers, -1, -2, -3, -4, -5, and the 0 in the center. On the other axis, we have only zeros, because we are always dividing zeros by some number, and we can divide 0 by every number, and will be still 0. Needless to say, all these numbers can be expressed with a finite decimal representation. Which numbers can't be expressed with a finite decimal representation? The first thing that I thought of was all the numbers where I divide by 3. And accordingly, all the numbers where I divide by 6 and 9. Every third row, so every third number. So the probability to pick one should be 1/3. But however, that's not all the numbers that has to be represented with a repeating decimal. There will be also the numbers in the 7th row, and in fact, from all rows where there's a prime in the denominator. And therefore, I thought the probability would be something similar to 1/3, because it's 1 out of 3 cases. I will pull some random number which is in a third row, plus 1/7, because with the probability 1/7, I will pull some number which is in a 7th row, plus 1/11, and so on. However, if you put that formula in the computer, it will easily say the probability is bigger than 1. In fact, for those of you who have had higher mass, it's diverging. And therefore, we did something wrong. The formula is completely wrong. And it's wrong because of 2.5 mistakes. To tackle these mistakes will be the main part of the course. However, before I want to start, I want to give you some moment to think about it and to try to figure it out by yourself. So please pause the video. 3, 2, 1, let's go. For those of you who are a little bit confused, let's consider 1/21. Give it a moment. Please pause the video. 3, 2, 1, let's go. First of all, 21 is a red number. It can't be expressed with a finite decimal representation. And it's counted, which is good. The problem is it's counted double. It's counted in this fraction, the 1/3, because it's in every third row. If we go up in pairs of 3, we'll see 1/3, 1/6, 1/9, 1/12, 1/15, 1/18, 1/21. And it's counted in the 1/7. So because we go up from 1/7, we go 1/14 and 1/21. So we have a problem that we count numbers double. This double count of numbers is the reason why we reach probability which is bigger than 1. And we have to compensate for it. We can compensate for it in our formula. If we take a look at this modulated formula, we see every third row still is counted because every third row is marked red. However, out of the 7th row, every third row is already counted. So we have to subtract it again. So we say 1, which is all 7th rows, minus 1/3, which is the number of rows that we already calculated. And therefore we have a compensated 1/7. This looks pretty easy. However, if we go to the next prime number, we will see we not only have to compensate for the 3rd row, however, we have to compensate it for the 7th rows. And not only for the 7th rows, but also for the compensated 7 rows. With that, the formula gets pretty messy. However, because it's recursive, you can easily do it numerically. In this case, I even did it with LibreOffice, which is a free version of Excel. So for the computer, it's super easy to calculate sums like this. And we will get that the probability goes to 1. A probability from 1 seems kind of strange, because obviously there are some numbers which can be expressed with a finite decimal representation. Why is the probability to draw them 0? And that brings us to our half mistakes. It's dangerous to talk about probabilities without a probability distribution. If we usually take a random number, we always have a probability distribution. For example, a Gaussian distribution, or even something like, think of a normal number between 1 and 10. It only allows a set of numbers. Here we have all the numbers and no distribution. So that's kind of strange, and we usually should not talk about probability then. So what we would rather talk of would be a ratio, or even better, a limit of a ratio, but that's might be too technical for this talk. So we will just talk about the ratio. and the ratio between the red dots and the blue dots. The numbers that can be expressed with a repeating decimal representation and the numbers that can be expressed with a finite decimal representation. Here I just name them red and blue dots, and the hashtag symbol is the mathematical symbol of counting. So the counts of the red dots divided by the count of the blue dots added with the count of the red dots. So the number of red dots divided by the number of total dots. So I was getting bored drawing these circles pretty fast, so I did some simulations and draw this diagram. The cool thing about the computer is that you can easily scale simple things like this. So if we make it bigger, it looks like that. And if you make it even bigger, it will look something like that. And here we see for bigger divisors, there will be more and more red dots. So if we go to infinity, there will be much more red dots than blue dots. And that's why our probability, or better, the limit of the ratio, is going to 1. So let's recap. We found one mistake, which was that we double counted numbers. If we correct it, we are still not done, because we should much rather talk about the ratio, or better, the limit of the ratio than a probability. But there's still one more mistake, and I want you to find it. So please pause the video. 3, 2, 1. Let's go. Before we get started, I want to give a little hint, as before. 6 circles that are drawn in the diagram below have the wrong color. Can you find them? Please pause the video. 3, 2, 1. Let's go. It's not sufficient to only look at the divisors to find out whether a number can be expressed with a finite decimal representation or with a repeating decimal representation. You also have to look at the dividend, because in some cases, like 3 over 3, the dividend cancels the divisor, and therefore we get an integer. An integer is expressed with a finite decimal representation. But even if we don't get an integer, like 3 over 6, which is a half, sometimes it can be expressed with a finite decimal representation. The other numbers that can be expressed with a finite decimal representation, which were drawn red before, on the other side, so negative minus 3 over 6, negative 3 over 3, negative 6 over 3, and negative 6 over 6. If we take this in our calculations and change the code, we will get something like this. It looks pretty, and we will talk about it in detail later. But first, we want to scale it to answer the question of the day, whether there are more numbers that can be expressed with a finite decimal representations, blue dots in this diagram, or are there more numbers that can be expressed with a repeating decimal representation, colored red. And we see for higher divisors, there will be a lot more red dots than blue dots. So we can conclude there are still much more red dots if we consider many numbers. So if we don't consider high divisors, for example, only divisors from 20 or below, there will be more numbers that can be expressed as a finite decimal representation. So it mainly depends on the range of divisors that we allow. This could be the end of the video. However, we have a pretty diagram in hand, so I want to talk about it. So let's take a closer look. If we want to understand some fundamentals in a really big and strange looking diagram, it's helpful to look by part. So we'll begin by looking on this diagram line by line. Let's begin. The first line, we already talked about it, are the whole integers. The next line is counting in halves. So 0, half, 1, 1.5, 2, 2.5, and so on. Needless to say, all these numbers can be expressed as finite decimal representation. So the next line was colored red before. Now we know every third dot must be blue because this line is a line where we divide by 3. So 1/3 must be expressed with a repeating decimal representation. However, 3/3 or 6/3, 9/3 can be cancelled. So we will get an integer again. The next line is dividing by 4. The next line by 5. Both of these lines, if we look at this as fractions, can be expanded with 25 or 2 to get an denominator of 100 or 10. Therefore, all these dots can be expressed with a finite decimal representation. The next line will be the 6th line. It looks exactly like the 3rd line because the 3 times 2 is 6. The 2 doesn't matter in the denominator. However, the 3 is the same problem with the 3. So every third number can be reduced. The last line I want to talk about in detail is the 7th line. We can see it's basically a red line where every 7th dot is marked blue. The explanation to this is exactly similar to the explanation I gave for the 3rd line. So every 7th dot, we can cancel a 7 with a 7. So this, for example, is 7/7, which is 1, and therefore an integer and can be expressed as a finite decimal representation. Same is true for all the other dots. If we take a closer look at the numbers, now we will express the numbers not only as before, like 1/7, 4/7, or 6/7, but after 7/7, we write it as the 1 plus 0/7. The next would be 1 plus 1/7 and 1 plus 2/7. This new way of writing it down is really helpful because the fact whether a number has a finite decimal representation or a repeating decimal representation doesn't change if we add an integer. So this attribute of the number will be only changed by the fraction that is behind the integer. And here we see everything is periodic because every 7 dots, the integer is changing and we go back to dots that we already had, but with a different integer in front of it. And as I said before, the integer doesn't matter for the color of the dot. So we could, in theory, reduce this diagram to a diagram looking similar to those, which looks much easier and less pretty. And we have the same number of dots, then we have the number in the divisor. So this is dividing by 1, so we have 1 dot. This is dividing by 4, so we have 4 dots. And this is dividing by 7, so we have 7 dots. And now we can easily count for every divisor what's the number of blue dots in comparison to all dots. So we can say in the 7th line, the probability to draw a number with a finite decimal representation will be 1/7. And the 6th line, it would be 2/6 or 1/3, and so on. This, for numerical reasons, speeds up simulations a lot because we don't have to consider a lot of dots, only as many dots as the number in the divisor. So let's bring up the whole diagram again and talk about other structures. The most prominent structure, in my opinion, is this V shape. Why do we have a V shape? Let's take a look at some numbers. This is 3 divided by 3, which is 1. This is 6 divided by 6, which is also 1. So you can see all those numbers are 1. So they're the same number. They're just a different representation of the number. We expand the fraction from 1 to 2 over 2 to 3 over 3, and so on. Same is true for the other side. All these numbers are minus 1. So now I have a question for you. If I mark some dots like this, there will be blue lines. Here we can imagine a blue line going through the whole diagram, and it will be continuing forever. Can you explain why? Please pause the video. 3, 2, 1. Let's go. A little hint. Take a look at some numbers. Check some numbers. What are those numbers? And try to figure it out. Please pause the video. 3, 2, 1. Let's go. All these numbers on the right side are 1/2. This first fraction is exactly 1/2. 1 divided by 2. The next would be 2 divided by 4. Then 3 divided by 6. And so on. We can reduce all this fraction to 1/2. And the other side would be negative 1/2. If we count them numerically and say this is 1, this is 2, this is third dot, and so on, we could write on an expression like this for all these dots. 1 times n, the number we are counting. And in the end, we could cancel the end, and then we see all these dots can be expressed with 1/2. And that's not just some strange line which we can find. We can find infinitely many lines like those. For example, this line. We go 2 to the side and divide by 5. So this line is 2 over 5. 2 over 5 can be expressed with a finite decimal representation. Therefore, the dot is blue. The next dot is expanding this fraction by 2. So we have 4 over 10, and accordingly so on. This brings us to a completely new understanding of numbers, because considering one line, we can always say on the right-hand side of this line, all these numbers are higher than that line. So all these numbers on the right side are bigger than 1, for example, 2. All these numbers on the left side of the line are smaller than the number. In fact, we can express any number with a line. So every dot that's crossed by that line is the same number, but in a different representation. So therefore, reducing a fraction is basically going that line to a dot closer to the center, to the 0, 0 point, which is out of the grid. Expanding a fraction is to walking that line above to a different fraction. And we can expand forever, but we can only reduce to the last point where the line goes exactly through here, the 1, 1, or the 1/2 in that line. Therefore, we can express every number with an angle in this diagram. It might be a weird expression of a number, but maybe it's helpful. So for those of you that already have a high school diploma, so it's a little bit more advanced, this question. What's the function of alpha that brings us from alpha to a number? Please pause the video. 3, 2, 1. Let's go. The function is function of alpha equals minus tangents with an argument of alpha minus pi over 2. It looks really strange, but because it's a tangent and it's point symmetric, we can pull in the minus in the argument. And then we call all the argument with the minus sign better, and we will get an easy function, which would be f from beta equals tangents of beta. But now beta is this weird angle, which is starting from the line we draw, and so then goes up to the divisor. The cool thing about expressing a number by an angle via tangents is that we can see that there are some numbers which cannot be expressed with rational numbers, which is really weird. For example, if we put in a degree of 30 degrees in beta or alpha, doesn't matter, we will draw a line which never ever reaches a point exactly. If you go to infinity, there will be some dots that are super, super close to the line, but there will never be exactly mathematically on the line. So there are a lot of numbers that are in between the rational numbers. They are called irrational numbers. The thing I want to end the video on is the question, if we don't consider these double numbers, if we say we only want to consider 1/2, not 2/4, not 3/6. All these numbers are redundant, we don't need them, we only need those numbers. If we delete all these points out of the diagram, or better to mark them yellow, what will we get? We will get a diagram like this. And here we see deleting double numbers, or better saying deleting equivalent numbers. We even see there will be much more numbers that can be expressed with a repeating decimal representation than there will be with a finite decimal representation. Here I want to end the video, but I have one last task for you. Can you figure out how to like this video and subscribe to my channel? 3, 2, 1. Thank you very much for attention. I'm glad you made it till the end. I hope you enjoyed it. If you did enjoy it, there's another video made by 3Blue Ron Brown. He's an excellent YouTuber, and here's the reason why I made this video. And the link video in particular has a huge influence on that video. So if you like mine, you will probably like this, which is a little bit more advanced in math, but even prettier. What I personally would recommend is to stop watching YouTube, go outside, play with some friends, and have a good day. Thanks for watching.